All right. My clock has ticked over to 7:30, so why don't we get started? Thank you for joining us tonight for our first lecture in the lecture series about the total solar eclipse that's upcoming. If you were here for the planetarium show, I hope you enjoyed the trip through space. My name's Andy Layden. I'm from the Department of Physics and Astronomy, along with Dr. Kate Dellenbusch. We're co-conspirators with some folks from the College of Arts and Sciences on this little project. And so we'll have sort of a 45-minute or so presentation from Dr. Dellenbusch and time for some questions at the end. We're zooming out to the live streaming via Zoom, and we're also doing our best to record this. So if you've got friends who weren't able to attend tonight, our hope, we're not sure yet that this is all going to work, because despite COVID, our technology is still not perfect. We're hoping to put a link to the video recording on probably the Eclipse webpage for BGSU, so you can point your friends to that. So let me take the opportunity to introduce Dr. Kate Dellenbusch. She received her bachelor's in astronomy from Cornell University in 2002. She went on and got a PhD in astronomy with a minor in physics from the University of Wisconsin at Madison in 2008. You may think of Kate as planetarium person extraordinaire. You may think of her as eclipse expert, but her graduate degree, her research specialty is in the stellar evolution of dwarf galaxies. So she's a person of many talents. She began teaching here at BGSU, teaching astronomy and physics in 2008. But her interest in presenting astronomy to the public at large has been with her probably, I think, most of her life, she would say. Sharing astronomy with the public, outreach events, telescope viewings. More recently here, she's become very deeply involved in the leadership of the Science Olympiad contests every spring, and is now, like I said, one of the principals in developing our total solar eclipse program. And I'm really impressed and grateful for Kate for taking up this fall the position of planetarium director. She's done a fantastic job sort of making a fast pivot to this role, and we look forward to great things, even greater things, as she moves forward. So I'm really pleased to present Dr. Kate Dellenbusch to lead off our Eclipse speaker series this spring. Kate?
Thank you, Andy. Yeah, so I'm excited today to kick off our lecture series. And if you've had a chance to look at the talks, I'll maybe mention a little bit more at the end, but we've got a really diverse group of speakers. And that's been one of my big goals for this series, is to show just how much of a human experience an eclipse can be. And so we wanted to reflect that in a lecture series with talks from history and music, literature, as well as astronomy and some other areas too. So I hope you'll come back for more as we continue. But today we're going to have kind of an overview and talk about what eclipses are and why we see them, and a little bit about how to safely view them as we start to gear up and get prepared for April 8th. So before we start that though, let's see if we can get on mute. There we go. Hopefully our little bar will go way up there so you can see the titles fully. But to lead into why we see eclipses, I actually want to start with thinking about the scale of the things involved. So as maybe mentioned a little bit earlier tonight, an eclipse of the sun and the moon, for that matter, involves the sun, the moon, and of course the Earth. And so let's get a sense of how big those three things are. And we'll start with the sun. We need to choose something to represent the sun. And I have this big giant beach ball up here. which is 42 inches across, about a meter across. And so we're going to imagine that this is the sun. We'll put that up here. And so now that's one of our objects. We know how big that is. But if we want to include the Earth and the Moon, right, we need to figure out what sized object we need to represent their appropriate scales. So let me sort of pretend we're in class here for the beginning a little bit and ask if anyone has any guesses how big the Earth might be. So if the sun is our beach ball, then how big do you have a kind of a size ball in mind that might represent the Earth on that scale? A golf ball, okay.
A grain of sand.
A grain of sand, all right, so we've got pretty big range there. And I think you've got it surrounded between the two of you. I've got a little tiny ball bearing on the end of a stick here, painted blue. And I guess I'll walk around once here. You guys can see a little blue ball. So that's how big the Earth would be if the sun were the size of a beach ball. Okay, so we think of the Earth as being pretty big, right, when we're standing on it here, trying to travel around the surface of the Earth. But compared to the sun, the Earth is pretty small. Right, well, that gives us the Earth, and I should bring up my size. So my little ball bearing, I'm cheating a little bit. It's 10 millimeters across. So it actually would be a little bit smaller than what we've got there. And now we also want to include the Moon here. And you probably know the Moon's going to be smaller than our Earth here. And in fact, even if I walk around, you're probably going to have a hard time seeing it. There's a little tiny ball bearing on the end of the stick. And it's even smaller than the stick, actually. Little gray ball there. Moon. But as moons go, our moon is actually pretty big. It's one of the biggest moons in the solar system. Little tiny moon. Small little moon there. Okay, so those are the three scales that we're talking about here in terms of eclipses. And I don't know, I should try to show them to the camera here. Okay, so that's great. We've got our relative scales in terms of how big everything is. But there's another piece that we need, and that is how far apart to put them. Okay, so if we want to get our separations correct, right, if we think about the distance between the Earth to the Moon, you can fit about 30 Earths in between the Moon and the Earth. And so in our scale model here, it'll be about 30 centimeters. I don't know, what's that? Maybe about like so. Right, well now, we also need how far away to put our beach ball. If we keep, let's say we keep the Earth and Moon here in the planetarium, where would we need to stick the beach ball sun in order to accurately represent that distance? Well, in fact, it's pretty far away, even though the sun is close enough, it keeps us relatively warm here on Earth, and it's quite bright in our sky. It's actually, even in our scale model, pretty far away. So it would be over a football field away, about 1¼ football fields away from where we put our Earth and Moon here in the planetarium. So we wouldn't be able to fit that here in the room. So that's one way to think about how big the Earth, Moon, and Sun are. But let's take another kind of way of thinking about it and putting it in a context that we're used to experiencing. And probably all have driven, say on the highway, maybe going at 65 miles an hour. And so if we were to think about going that fast in our car, and if we could drive all the way around the circumference of the Earth, then how long would it take us? Well, if we're going at 65 miles an hour, it would take us, wrong light there. It would take us about 16 days to go all the way around the circumference of the Earth. right? We get that sense that Earth is pretty big, right, on our kind of normal movement terms. Well, if we include the moon here, we do the same thing. If we brought our car up to the moon and we drove around the moon, well, even the moon would take us over 4 days to drive all the way around, going at 65 miles an hour, about 4 days and 8 hours. Well, if we could go to the sun and survive the heat and kind of do the same thing, drive all the way around the sun, well, its enormous size, right, the big giant beach ball compared to the Earth and moon there, it would take us almost 5 years to drive all the way around the sun. Right, now let's use our same idea of driving at 65 miles an hour and include our separations here. So if we were to drive at 65 miles an hour from the Earth to the moon, well, that would take us about 153 days. Right? There's a reason rockets are going a lot faster than 65 miles an hour. Well, more than one, but one would be take a really long time to get even just to our near neighbor of the moon. And if we want to drive the whole 93 million miles to the sun at 65 miles an hour, well, that would take us 163 years to get to the sun. Well, another way to think about just how far away the sun is that even light traveling at the speed limit of the universe, no information gets carried faster than the speed of light. Even that, covering the distance from the sun to the Earth, takes about 8 minutes. So when we look up at the sun, we're really seeing it as it was 8 minutes ago because it's taking that long for the light to reach us. All right, so we've got a little bit of a sense of the objects and the scales involved in an eclipse, but eclipses really are about shadows, right? And what's casting a shadow on what? And so we need to think about what is our light source? Well, of course, that's the sun. And then we want to think about, well, what object is casting the shadow and where is that shadow falling? And as I've mentioned earlier tonight, a solar eclipse is occurring when the moon is in between the sun and the Earth, so that the moon's shadow is falling someplace on the Earth. Right, so before we look at that in some more detail, though, let's think a little bit more about what shadows are like. And if you've ever looked really closely at a shadow, maybe when you're outside or something, looking at your own shadow or another object shadow, you might notice that shadows aren't actually uniformly dark, that there's a dark inner part of a shadow and a lighter outer part of the shadow. And so in the picture here, I just used a pencil eraser that I'm standing up there and shining a light at. And we can see, right, the kind of rounded end of the eraser there. And so the eraser, it's blocking some of the light that's shining past it. And within this whole region in here, it's really blocking all of that light. And so we've got this dark inner part of the shadow. It's called the umbra. And then out here, this weaker part of the shadow, which is called the penumbra, right there, a little bit of light is getting past our eraser in this case. And so some light's getting there, but not all the light that would if the eraser weren't there. Right, so if we put that in the context of an eclipse, right, where we've got the moon, right, basically a ball, and we've got the sun shining its light at the moon, right, it's like having a flashlight here and a ball. And so we can see that in here, we've got that dark inner part of the shadow, the umbra, right, where all the light from the flashlight's being blocked. But out here, if we think of, say, a point of light coming from this part of the flashlight, it's still able to make it over to this region. But light from over here, right, that is being blocked by the ball. So as a result, in a circle around our dark inner circular shadow, there's this lighter penumbra surrounding that dark inner part. Right, so just like with the eraser, the same thing is going to happen with the moon. Right, so that means that for an eclipse, we've got this kind of setup for a solar eclipse where we've got the sun over here. We can see this isn't really to scale. We've seen how much bigger the sun is than the moon and the earth, but to make it fit on a slide and kind of see what's going on. Well, we've got the sun over here. Here's the moon. And so the moon is blocking light from the sun and casting its shadow on the earth. And even though this isn't drawn to scale, you can maybe get the sense that that dark inner part of the shadow that's falling on the earth is really small, right, compared to the size of the earth itself. Right, so if we happen to be on the surface of the earth within that dark inner part of the moon's shadow, then we're going to be able to see a total solar eclipse. And as we'll talk more about here in a little bit, if we're in the outer, weaker part of the shadow, we'll get to see an eclipse, but it'll just be a partial eclipse. Right, so to help us visualize what's going on there and get a little bit better sense of the scales, we've got a little animation from NASA here. We'll bring down the lights since part of it's dark to see the moon's shadow here, so hopefully it's a little bit easier. But basically we're going to kind of fly around the earth and the moon and look at where the shadows are falling. So here's the moon's skinny shadow. And we're going to see that for this upcoming eclipse, that shadow is going to track across this band of the United States. When it hits land in Mexico, and then up to Texas, and across the United States, including up through here in Bowling Green. So I'm going to pause for a moment. I get there fast enough. Right, so we've got this dark or this red strip, which is the path that the inner umbra is following, where totality is visible. And then in purple, here's that outer, the edge of the outer weaker shadow. So everybody else basically in the United States is going to see a partial eclipse, but only along this special strip will we get to experience totality. All right, we'll continue on here as we zoom out and see the moon's really long, skinny shadow that's just barely hitting a part of the earth. Oops. We'll back up just a little bit. All right, so hopefully with the lights off, you can see here's the moon, here's the earth, here's this long, skinny shadow that's just hitting the narrow little strip of totality, and giving us a sense of just how special of an event this is for any particular location on Earth to be able to see a total solar eclipse. All right, good. Bring up the lights again. Right, so we've got most of the pieces that we need to think about eclipses, but there's still another piece that we haven't really talked about. And that is, from our perspective on Earth, how big does the moon and the sun look, right? So what are we really going to see as we look up at the sun safely during an eclipse? Right, so during an eclipse and these casting of shadows, right, it means that basically we've got all three things lined up. We've got the sun, Earth, and moon. Well, sun, moon, Earth in that order, all perfectly lined up in a row, allowing us to see an eclipse. But there are other situations where things might also be in a line, but they won't look like what we see as a solar eclipse here on the Earth. So one possibility would be that we have something that looks big to us, and it's passing in front of something that looks smaller. And when that happens, that's called an occultation. And so in the picture here, we've got the bigger looking moon passing in front of a pretty small looking planet Mars there. Right now, really, the moon is smaller than Mars is. And we'll come back to why it looks so small compared to the moon here in the picture in a moment. But right, for an occultation, we've got something that looks big that's passing in front of something that looks small. But we could also have the opposite situation where something small is passing in front of something big. And when that happens, we call that a transit. And so, for example, from Earth, we see primarily that being Venus or Mercury passing directly in front of the sun. So every once in a while, everything lines up just right. So from our perspective here on Earth, we see either of those two planets passing directly in front of the sun, in which case that planet is blocking a little bit of sunlight. Right? It'll look like this. This is Venus transiting across the sun. Right, but then for an eclipse, right, we also have things lined up. But in this case, not only that, but one object is casting a shadow on another. And so from Earth here, we get to see solar eclipses as these really unique special events where the moon is directly lined up and covering the disk of the sun. Right, but we just saw that the moon is very, very different in size from the sun, right? The little tiny ball here compared to the big beach ball. So there's one more thing that we need to take into account to think about an eclipse. And that is how big things look to us, or what we call the angular size of something. But basically, how much of an angle, how much of our field of view does an object take up? Right? You probably intuitively have noticed or observing throughout your life that when something is close to us, it looks big, and when it's far away, it looks smaller, right? Even if it's the same object, right? If you're standing right next to the house here, it's taking up your whole field of view. But if you're a block away, the house looks much smaller. It's got a much smaller angular size. Right, so that's true for the moon and the sun as well. And even though they're very, very different in size, they're also very different in distance from us. And so it just happens that where the moon is and where the sun is and how big they actually are, from our vantage point here on the Earth, they both look the same size. They both look like they're half a degree across. And so that means when things do line up just right, then the moon is perfectly in front of the sun and blocking basically all the light except for the outer atmosphere of the sun. There is one other complication, though, which we sometimes see reflected in the type of solar eclipse that we get to see. And that is the fact that the moon's orbit isn't perfectly circular. So sometimes the moon is a little bit farther away from us than it is at other times, so that even if everything is lined up just right, the moon's not quite looking as big as the sun does in our sky. And so here we've got a couple of pictures taken of the moon when it's at its nearest and farthest from us. And so there's not a huge difference, but it's about a 12% difference. Right, and that's enough so that an eclipse looks very different depending on which case we have. So that when things are lined up exactly right, we might have a case where the moon's looking a little bit smaller. And so even though it's perfectly in front of the sun, its angular size is a little bit less than the sun's. And we can still see this ring of the sun visible around the moon. And this is called an annular solar eclipse, for an annulus or ring. In fact, if you paid attention to the eclipse that was visible across the United States in October, from the best place to view that eclipse, that was an annular eclipse. So it looked like this. From here in Bowling Green, it was cloudy, but we would have seen actually a weaker partial eclipse like this. And then if things are at just the right distance, as well as being lined up, then the angular size of the sun and the moon match each other, and we get the special total solar eclipse, which is what we'll have coming up on April 8th. Right, and then sometimes if you're not in the right place on the Earth, or even occasionally just the way things are lining up and kind of where the Earth is, we might, instead of having an annular eclipse or a total solar eclipse, only see a partial solar eclipse. Right, so let's come back to our kind of thinking about shadows and what's going on in each of these three cases, and what you'd see where, depending on where in the shadow you are. So let's start with the case of the total solar eclipse. As we've talked about, the moon's shadow has this dark inner part, the umbra, and then the weaker outer penumbra. And so if we happen to be on the surface of the Earth, right within that dark inner shadow, then we'll see totality. If, though, we're out here in the penumbra, in the weaker part of the shadow, then we only see a partial eclipse. And how close we are to the umbra determines how good of a partial eclipse we see. And then in the case of the moon being a little bit too far away for us to get a total eclipse, then the moon's shadow in some sense isn't quite getting to us, and we're actually within what's called the anti-umbra. And then we'll see an annular eclipse with this ring of sun still visible. And if we're not within that region, we're out here in the lighter part of the shadow, we'll again see just a partial eclipse. So we've talked somewhat abstractly and looked at a eraser shadow, but what does this actually look like for the moon? Well, this is an image taken from Earth orbit during an eclipse, and you can see this dark inner part of the shadow. So folks in there get to see totality if it's clear out. And then you can maybe see out here, the shadow looks weaker. So these folks will have just a partial eclipse. And you can maybe tell that the closer you get to the umbra, the kind of darker it becomes. And so they're seeing a better and better partial eclipse until you're within that zone and you've got totality. And then for everybody else on Earth outside of the shadow completely, it's just a normal day and the sun isn't eclipsed at all. So we've talked a little bit about how special a total solar eclipse is. And in terms of how frequently they happen, they do happen someplace on Earth about every 1.5 years, 2 years. But because the strip where totality is visible is so narrow, since the moon's shadow is really narrow, then in order to see totality, you really need to be in just the right place. And because of that, from an individual location, they don't happen very often. And so in that sense, we've got really a once-in-a-lifetime opportunity to see this eclipse. And the next time a total eclipse will be visible from Bowling Green in Northwest Ohio won't be until 2099. So if we want to see another total eclipse, we need to travel someplace else on Earth. And this diagram is pretty busy here, but these are the paths for all of the solar eclipses between, I think it's 2021 and 2040. My dates are covered up there with the zoom bar at the top, but if I remember right. And so if you, oh no, actually, oh yeah, I guess it is 2021. So the path for the annular eclipse in October was this path here. And then the total eclipse coming up in April will be along that blue track, right? So as the Earth spins on its axis and as the moon's moving a little bit in its orbit, the path of the shadow tracks across a strip of the planet, right, where it's not just one individual location, but everybody along that path will get to see the eclipse. And with kind of one following after the next as the shadow moves along. Well, you can get a sense, of course, that since the Earth is largely oceans, that many of the eclipses are visible from oceans, maybe even more so than the continents. And so there are actually even eclipse cruises that happen where they'll sail to where the eclipse is visible. And I don't know, maybe that's easier to go find a hole in the clouds if it's cloudy and might have a better chance of seeing it. But hopefully we'll luck out here on April 8th, even though it's Ohio April weather. We'll all keep our fingers crossed for clear skies, at least for a little while that day. So let's look a little bit more closely at those tracks for those two eclipses, the October eclipse that just happened and the upcoming April 8th eclipse. So this is the path of that annular eclipse in October. And Texas, I guess, is kind of the place to be for this eclipse season of these two eclipses. But here we've got this path of totality for April 8th. And if you look at kind of what that path is like, right, we can see that this is covering a good stretch of the United States. We'll be able to see totality. In fact, especially within where a lot of the population centers are. There are a lot of big cities along the path or quite near the path. And so it's expected that there's going to be a lot of travel, even if it's people just coming, right, a state or something over or less than that, to come into the path of totality. And so if you've heard about the predictions of difficulty driving on eclipse day, that's why. So we're trying to promote the idea of come early and stay late. If you're going to come and join us at our watch party here in the stadium or wherever you might be viewing the eclipse, if you're traveling, to come early and then stick around even after totality, so that we can try to ease those traffic burdens and people aren't stuck in traffic for hopefully quite as long. All right, so now if we look just at the path of totality for April 8th, it's a little bit easier to see than it was on the previous diagram, but you can maybe notice these lines that are kind of parallel to the path of totality. And that's showing us how good of a partial eclipse they're going to see. So if we're here in the path of totality, that's really a special thing, and no partial eclipse compares to that. So if at all possible, you want to make sure that you're within the path of totality. But the closer you are, at least the better of a partial eclipse you're going to have. And so we can see, right, the farther you get away, they're seeing a less and less of a bite being taken out of the sun. And then for us in Ohio, this is the path of totality. And so it goes in terms of the southern extent of it, the northern suburbs of Columbus will be within totality. And then it's just kind of up through Toledo, northern Toledo. And everything in between then is going to be able to experience totality. This center line that's drawn on here, that's the ideal spot to be for the total eclipse, where totality will last the longest for kind of that region of the country anyway. And so we're not quite on that center line, but we will have about 3 minutes of totality from here in Bowling Green. And by comparison, if we went down to Wapakoneta or so, they're close to the line of or the center line, I think they've got about 3.5 minutes. So we still have a pretty good long totality as totalities go at 3 minutes. Okay, so before we look at a few pictures of what we'll see and how to view an eclipse safely, I want to talk about one other thing that's important for understanding why eclipses don't happen all the time. And well, maybe one of the future talks will talk about this in a little bit more detail than I'll do here, but we'll get the basic idea. And so if you know about why we see different phases of the moon, then you might recognize that, well, if we're seeing a solar eclipse, the moon is in the same direction in the sky as the sun. And so that's what we have when we have a new moon. And then if the moon is on the other side of the Earth from the sun, opposite the sun, then, well, that happens every full moon. But we certainly don't get an eclipse, a solar eclipse and a lunar eclipse every month, right? They happen much less frequently than that. And so there must be something else. It's not just that moon and Earth and sun are kind of in the right order. But we don't get them all the time because the moon's orbit is tilted just a little bit compared to the Earth's orbit around the sun. So here on the diagram at the top, this blue line is the plane of Earth's orbit around the sun. And here we've got the moon's orbit, the gray line there. And so the moon's orbit is tilted just a little bit, just 5 degrees from the plane of Earth's orbit. But that's enough so that most of the time, the moon's little tiny shadow isn't falling on the Earth, or even that the Earth's shadow most of the time isn't falling on the moon, so we don't get lunar eclipses all that often either. Most of the time, the moon shadow is above or below the Earth, and so we don't get to see a solar eclipse, right? It would have to be somewhere out in space in order to see that eclipse. Right, I've got a little animation to help us see that in motion as well. So we're going to start off with a view from above. Here's the moon moving in its orbit around the Earth. But if we look from the side, right now we can see plane of Earth's orbit. And so most of the time, the moon shadow is falling above or below the Earth. And so we're not going to see an eclipse. But every once in a while, things are just lined up exactly right, and we get these magical special eclipses. All right, so what are we going to see, hopefully, on April 8th? Well, as the moon is passing along in front of the sun, we're going to see bigger and bigger bites taken out of the sun over time until it's lined up just exactly in front of the sun. And at that point, we have this special totality where the moon is fully covering up the disk of the sun, and this kind of whitish halo that you see around the sun, that's the sun's outer atmosphere, which is comparatively much, much fainter than the rest of the sun. And so most of the time we don't get to see that corona, as it's called. And during an eclipse, a total eclipse, though, we can see that just without any special instruments to kind of artificially create an eclipse. So that time of totality just lasts for a very short time. As I said, 3 minutes in the case of this eclipse for us. And so, right, it's constantly moving along. And then for the kind of end of the eclipse, or the second half of the eclipse, we see now more and more of the sun becoming visible again until it's back to not being eclipsed at all, and it's just a normal day once again. And one of the things that we can try to observe during an eclipse is what the corona looks like. And I think Andy's going to talk more about that in his talk next week. And so the shape of the corona isn't the same all the time. And so you see some of these different eclipse, total eclipse pictures. You'll see that there's variation there in the shape of the corona. All right, so what do we need to be prepared for in terms of viewing the eclipse safely, and what time are things going to happen? Well, for us, the eclipse will start around 1:56 p.m. With the moon just starting to contact the sun, what we call first contact, where it's just starting to sort of pierce the sun there. And then that first half of the eclipse, as the moon moves across in front of the sun, will continue until totality starts at 3:11 for us and last until about 3:14. And then after that, now we've got the second half where more and more of the sun is becoming visible again. And so that'll continue until about 4:26 p.m. if you want to stick around and keep an eye on the whole process there. This graphic that we've got here is something that we'll be putting out more as we get closer to the eclipse to remind people to safely view the eclipse. And so during the partial phases of the eclipse, we need to make sure that we're protecting our eyes. The sun is really, really bright, and even just a second or two of looking at the sun directly without protection can damage our eyes even permanently. And so during the period before totality and after totality, we need to make sure that we're using eclipse glasses or other filtered instruments or pinhole projection that I'll show some examples of during that time, so we're viewing it safely. And then during totality, though, we actually want to take our eclipse glasses off, or you'll miss all the excitement of the faint corona. And we just need to be careful that we get them back on right as soon or maybe a little bit before totality ends so that we're safely protecting our eyes once again as bits of the sun become visible. All right, well, what can we do to view the eclipse safely? One thing would be to use so-called eclipse glasses, which we've got these BGSU Falcon eclipse glasses. And anyone who wants to come to the stadium to view the eclipse will have a pair of glasses. We've got a lot of pairs that we need to hand out. So come and get one on Eclipse Day. And with these glasses, it's really just a cardboard frame. And there's some material here called mylar, which blocks enough of the light from the sun so that it's safe to view the sun. So we can use those. But we can also look at the sun instead of directly through projection. And there are several ways we might think of doing that. One would be actually just using nature itself, although in April it would be a little bit harder. But if you've seen even a partial eclipse before, when there are leaves on the trees, if you look underneath the trees, you'll see all these little crescents, like in the picture there, where little pinholes in the leaves or in between the leaves are acting like a pinhole camera, where light's filtering through, and you get a little tiny image of the sun. So you can see the eclipse in that way. And for our event at the stadium, we're going to try and make some displays that have pinholes, probably even as letters of BGSU and things, if you want to go and take a selfie with a bunch of crescents all over you, things like that. You can do so, since we won't have leaves on the trees and no trees in the stadium. So we'll make our own little pinhole projectors to do a similar thing. And then you can also make another kind of pinhole projection device to safely look at the sun with a cardboard box, for example, where you can put a white piece of paper or screen at one end of the box, and you've got a little pinhole at the other end of the box. And so you look towards the white screen, so you're not looking straight at the sun. And just like with the leaves here, you're getting a little tiny image of the sun. And so that's great for watching the eclipse kind of progress as we see a bigger and bigger bite taken out of the sun, or more and more of the sun becoming visible after totality. Right, so you can use pretty much any box that you like to do that. The one that I've got up here is just an ordinary cereal box, where I've cut out a little hole here for me to look into, and there's a little pinhole. So you stand with your back towards the sun, put the bigger hole facing, or I'm sorry, the pinhole kind of lined up with the sun. Takes a little bit of practice to get it lined up. And then you look in at the white screen at the bottom through the bigger hole and see the pinhole projection. And if you'd like instructions on how to make a cereal box viewer, we've got those instructions on the BGSU Eclipse website, and I'll have the URL up here in a moment. Right, so just to recap our safe viewing here, we want to wear eclipse glasses or use pinhole projection before totality. Look straight at the sun during totality to see the special event, and then use our glasses again the rest of the time after totality. All right, so to wrap things up here, I just want to mention a little bit about the rest of the lecture series. And either if you were here for the planetarium program, have that in the program, or we've got some cards up here as well if you want to take one of those. And so every Thursday until the eclipse, so through April 4th, we'll have a different lecture. And all but one of them will be here in the planetarium, and all but two are starting at 7:30 for the lecture portion, like tonight. The two exceptions are we've got a special collaboration with the history department and their Redden Symposium. So there'll be a number of speakers, and that will be held at the library downtown. And so that's going to start at 6 and last a little bit longer. And then so that's on February 22nd. And then on February 29th, we've got a special kids program for young kids in collaboration with WBGU. And so we'll hopefully have some activities and things that kids can work through what eclipses are, and maybe helping them make some paper plate kind of holders for their eclipse glasses, so it's safer and easier for them to use the eclipse glasses. All right, and as I said, we've got a number of programs related to music and literature and art, as well as astronomy and history. Okay, so if you're interested in knowing more kind of little descriptions of each of those lectures to see if it's interesting to you and you want to come, or to see what other eclipse related events we have going on leading up to the eclipse, as well as more about the watch party at the stadium, you can check out the BGSU Eclipse website there. It's pretty easy, bgsu.edu/eclipse. And there's a link for the calendar of events as well. And I'll mention for anyone who might be interested, we're also looking for people who've got some idea for sort of an exhibit or activity that people can participate in at the stadium as well. So again, we can help encourage people to stick around longer than just the 3 minutes of totality. So we want to have things for people to do. And there's a registration form if you want to propose an idea on the website as well. All right, thank you. I'll see if there are any questions. Yeah.
Can you go back to the slide where you can see different paths of totalities for partial eclipses?
This one here? Yep.
So I see the narrow strip of the totality is going to go to our region, right? And it ends, I see it ending somewhere in the Atlantic.
Yeah.
Now, of course, at that time, it's going to be night in Europe, and you're not going to see the eclipse anyway. But theoretically, the eclipse would be white.
Yeah, so in order to see the eclipse, right, we need to be facing the sun and the moon for us to see everything lined up. So yeah, certainly if we're on the nighttime side of the Earth, then we're not looking the right direction. So since we can't see through the Earth, we can't see the eclipse from there. Yep.
And can they have the next one?
All right. Other questions? Yeah.
What branch of math is it that studies or predict all these times?
Yeah, so the question, I should be repeating for the Zoom, I'm sorry, is about the branch of math to predict eclipses. So predicting eclipses historically was a pretty hard thing. And so for a long time through human civilization, it was a scary thing, right? Suddenly the sun is going away for a few minutes and people weren't always sure if it was going to come back again. And so there are lots of stories about, is it a dragon eating the sun, or right, how do we scare the dragon away to let the sun come back? And since an eclipse, a total eclipse especially, you really have to be in the right place on the Earth. And so even though eclipses are happening someplace on Earth, if you're just in a fairly narrow geographic region, you're not going to know that another one has happened. So it was hard to figure out what that cycle was of really how often they're happening. But eventually, right, humans are pretty good at seeing patterns and things. And so even if they didn't know exactly what was going on and why they were happening, just by seeing that pattern, they were able to work out kind of a type of frequency with which they would happen or be visible from their location. These days, we know the orbits of the Earth and the moon really well. And so it's possible to really easily, effectively calculate when they're happening, but there are lots of subtleties that make it harder. Even things like, what is the topography on the surface? Are there hills or mountains? So exactly what time totality is going to start from a particular location. There are a lot of other complicated things, topography, the atmosphere, things that have to be taken into account if you're going to get it down to the second of when totality is happening. But basically celestial mechanics is the basic ideas of how the orbits work. Other questions? Yeah, let's go over here first.
Usually go back to the slide where it shows that this is
Which I'm not sure.
okay,
This one or
one more. So if you were in the on a tumbler, if you were to like fly or raise up like a camera high enough, could you get the totality within that pocket?
I think it would not be on Earth where it would be the case. Yeah. So in principle, you could go partway to the moon, and that would be true. Yeah. I don't know off the top of my head what that distance is, though, necessarily.
So in that triangle that is wide, we see no eclipse at all, right?
In the white part here, you would see an annular eclipse, so it's going to look like this. So things are lined up, but the shadow isn't kind of directly falling on the Earth, but you're still within this region where the moon is directly lined up with the sun. So it still is in front of the sun, still covering most of the sun, but not quite all. Yes.
Can you use the glasses and then look through binoculars or a telescope or anything?
So if you want to look at, so the question is about using binoculars or a telescope to view the eclipse. You can do so, but you do need to be careful. You need special filters covering the lenses on the binoculars or the telescope. Basically, kind of a big version of what's in the eclipse glasses to do that. And so at the stadium, we will have some small telescopes set up that have those correct filters and some other ways to view the eclipse, so we can see the image of the sun bigger than we would with just our eyes or with our pinhole cameras. But even for these days, we all want to take pictures of things with our cell phone cameras. And so just like we need to protect our eyes in looking at the sun, the same thing is true of the sensor, our camera in our phone. And so if you want to take pictures other than at totality, you need a similar kind of filter, whether that's holding up another pair of glasses, right? Keep one on your face, but another one in front of the lens on your camera. Or there are some bigger kind of versions of this that make it a little bit easier to make sure that you're covering up your camera lens as well. So yeah, those are things that we need to think about if we're taking pictures or trying to use other tools to look at the eclipse. Yeah, we might have some questions from the chat. Is that?
Actually, I was just going to add on to your response there real quickly. You're thinking about putting the eye protection in front of your eyes, but gathering light with the binoculars may end up damaging the binoculars. Kind of think like a magnifying glass to start a fire, right? You concentrate a large amount of light onto a small spot, and so you can melt the plastic or other components inside your binoculars. So you may not hurt yourself, but you're very likely to hurt your binoculars or your telescope. So
yeah, and usually even if we're using a little bit bigger telescope, like for example, when I was a kid, I was doing some eclipse outreach, and I had an 8-inch telescope that I brought to show people the eclipse. And so to make it safe to view that, I had some mylar to make my filter at the end of the telescope, but to let even less light into the telescope, I used cardboard to mask down the telescope. So the actual kind of size I was using was more like this. So I'm covering most of the aperture of the telescope and just letting a little bit of light through, and even that through the filter to make it not damage my telescope and be safe. Hey, any other questions? Yeah.
At the beginning of your lecture, you referred to nighttime and shadow. You said that twice. I have a hard time understanding. Why is night shadow?
I'm not sure what you remember, or if I misspoke, but so nighttime, right, when we're experiencing night on Earth, well, in some sense, we are sort of in the Earth shadow, right? But basically, we're facing away from the sun, so we're on the half of the Earth that's not being illuminated by sunlight. So the Earth is in the way, and so we aren't seeing the sun, and it's nighttime for us. So during a solar eclipse, we are looking in the direction of the sun. It's daytime for us, right? But the moon is in the way, and it's blocking most of the light from the sun. So we get a few minutes of kind of really dark twilight during totality.
Exactly.
Oh, okay. Was there some
Exactly.
text in the?
But now I think I understand the concept now. When the sun is behind us, the space right where we are is not illuminated at all, and therefore it's dark. But if we could see right ahead of us, we would see the shadow of the Earth in a way. And we can't see anything because it's extremely dark, but it's still a shadow.
Yeah, so at nighttime, right? Well, this diagram isn't ideal, I guess. Let's see if I can.
Well, I wasn't.
I'll find another or a little
I think I understand.
cartoon version here. Yeah, maybe this one is good. So yeah, the sun, right? It's off over here somewhere. And so here we can see it on the moon and the Earth here, that half of it is shaded dark, right? The half that's facing away from the sun. So this would be the nighttime side of the moon, right? This would be the daytime side, and same for the Earth here. So the half of the Earth that's facing the sun, folks there have daytime, and the other half of the Earth is facing away from the sun, and they've got nighttime. But, right, that is the direction of Earth's shadow too. So in some sense, right, we are within the shadow of the Earth. We're just on the surface. Okay. Any other questions?
So are they able to predict what the corona is gonna look like, shapes of? Like, I thought you mentioned different shapes.
Yeah, so the shape of the corona and appearance changes based on what the magnetic fields on the sun are doing primarily. And so we do have ways to see the corona even when there isn't an eclipse. We kind of artificially put kind of a disk in front of the sun in instruments and telescopes to view the corona. And so, yeah, it is being monitored kind of all the time, essentially. So we've got pictures frequently of what it looks like. So I'll have some idea maybe what to expect if any of those images have been taken recently. But yeah, from an individual viewing a total eclipse, you know, or multiple total eclipses, each one is going to be a little bit different and look different for them, since the sun was a bit different each time. Okay, Andy, do we have any questions in the chat?
No.
No? Okay. Any other questions here? All right. Well, again, thanks everybody for coming, and I'll hope you come to another one.